Hi, Glass. In this recording, we're going to talk about myelin, that chemical or that substance that electrically insulates the axons of neurons. And we're also going to talk about how myelin influences the conduction speed of action potentials. So, as we dive in here, let's talk about our myelin. When we think of myelin, it insulates the nerve fiber. It insulates the axon of our neurons. Within the central nervous system, it's formed by oligodendrocytes. Within the peripheral nervous system, it's formed by Schwann cells. And as we look at the myelin, it has its white coloration because it's overwhelmingly going to consist of lipids. And when we myelinate something, the process of myelinization typically begins at about week 14 of fetal development, and it happens pretty quickly during infancy, and then it's completed during late adolescence. As we look at this process of myelinization, it depends upon dietary fat. Myelin is mostly lipid. So if we don't get that fat in our diets, we are going to have a hard time getting the correct amount of electrical insulation, the correct amount of myelinization within our nervous system. As we're looking at the peripheral nervous system and the PNS, Schwann cells start off by sandwiching themselves around the axon or nerve fiber. And then as they're sandwiching themselves around the nerve fiber, they continue to corkscrew around until the Schwann cells wrapped itself around the nerve fiber many individual times. And then wrapping around that nerve fiber will have the outermost layer of the Schwann cell, known as the neurolemma. And this neurolemma is going to contain the nucleus of the Schwann cell and the cytoplasm of the Schwann cell. And then superficial to that, we have another layer known as the endoneurinium. This endoneurinium is an electrically insulating layer that goes all the way around the nerve fiber, around the Schwann cells, and around the gaps of the nerve fiber where there is no Schwann cell. Within the central nervous system, the oligodendrocytes do a similar process where they will extend a pseudopod or false foot, and that pseudopod will then migrate around and wrap itself around, spiraling around one individual section of the axon of a neuron or a nerve fiber. A key difference between the oligodendrocyte and the Schwann cell is an oligodendrocyte will be anchored to multiple nerve fibers, where a Schwann cell will only be anchored to one. It's also worth emphasizing that the oligodendrocytes cannot migrate around nerve fibers. They can't move around. They're pretty stationary due to the fact that they have multiple attachment points to multiple nerve fibers. And as we're looking at this process of myelinization with an oligodendrocyte, they typically are going to have to push new layers of myelin under the older layers of myelin. So as we're looking at this process, myelinization spirals inward with the oligodendrocyte as opposed to spiraling outward with the Schwann cell. And within the within the central nervous system, nerve fibers themselves in the central nervous system, the CNS, do not have a neurolemma or an endoneurinium. So if we're looking at the neurolemma, or it can't be a neurolemma because the nucleus of the oligodendrocyte is over here, completely separated from the Schwann's, or completely separated from the nerve fibers. And if we're looking for the endoneurinium, the endoneurinium is not present because we are instead going to have other cells of the central nervous system electrically monitoring the cerebrospinal fluid so that we can have good control of the electrical activity of the axons. Now, as we're looking at the Schwann cells and the oligodendrocytes, we need lots of them to cover one axon. One single axon can be up to 30 centimeters long. That's quite big. And as we're looking at this myelin, or these nerve fibers, we're going to have a myelinization point, and then we're going to have a little gap, and then another myelinization point, followed by another gap. The gap is referred to as a node of Ranvier. I remember when I was in college, there was a heavy metal band that I listened to called the Node of Ranvier. I got a kick out of that. And in between at those, in between nodes of Ranvier, we're going to have myelinated sections. And those myelinated sections can be referred to as the internodes. Here, if we check out a photomicrograph, we can see a myelinization point, there's a Schwann cell within a nerve. Here's another Schwann cell, and that little gap right in there is a node of Ranvier. It's also worth emphasizing that there's an initial segment. The initial segment of the nerve fiber is located right here. It's at the very beginning of the axon, located by the axon hillock. And then finally, we have the trigger zone. Our trigger zone is going to be the part that initiates the action potential. So when we start having action potentials, the trigger zone, or where the action potential starts, is going to be right there at the beginning of the axon, and then it'll travel the length of the axon and then get to the axon terminals, be converted to neurotransmitters, which then will jump across to the next cell. Now within the peripheral and central nervous systems, we're going to have myelinated and unmyelinated fibers. Oh, excuse me. Oh, I need to drink more coffee. So within the peripheral nervous system, we're going to have unmyelinated nerve fibers can be enveloped by a Schwann cell partially. So the Schwann cells can have 1 to 12 small nerve fibers just embedded in their surface. So as we're looking at these nerve fibers, these excuse me, that was not a nerve fiber I pointed to. Here we go. There's a nerve fiber. There's a nerve fiber. You can see there's a little gap. That little gap is going to allow the nerve fiber to be exposed to the same environment that is underneath the endoneurium. So as we're looking at this process, we're going to have a continuously exposed surface membrane of the nerve fiber within the peripheral nervous system. And as we're thinking about conduction speeds, the myelinization point, or how myelinated it is, influences the conduction speed. If we have myelin present, the action potential, the electrical signal, jumps from node of Ranvier to node of Ranvier. This is referred to as saltatory conduction, as it's jumping from node to node to node. And you can think of the myelin sheaths as acting as capacitors. Another thing that influences the rate of conduction is the diameter of the nerve fiber. Wider diameters, larger fibers have more surface area. More surface area is going to be able to more efficiently and quickly propagate the action potential. So let's get some numbers to this. If we have a small unmyelinated fiber, the action potential can move up to 2 meters per second. If it's small and myelinated, the action potential speeds up to 15 meters per second. And if it's large and myelinated, it can go up to 120 meters per second. So when would we want slow? When would we want fast? Slow signals are typically going to be reserved for the gastrointestinal tract, or areas where we don't need a lot of speed. And sometimes slow and steady is more important than having fast and instantaneous communication. We save our fast signals for areas like our skeletal muscles, where we need lots of speed. We need to make lots of small corrections very quickly in a very short period of time so that we can be coordinated and not fall over. That's all we have for this recording on myelinization and how it influences the speed of action potential conduction. If you have any questions, please post them in the course discussion board or feel free to shoot me an email. And as always, happy studies.